expand on in this class. Largely, I hope that relatively nice. Before we do that, probably saw in well, right? Quick exam, efficiency factors are due. Couple technical well. So if you haven't done those yet, you get them to try there, multiple and those are for the scale phase, right? So next, we're going to be talking about the chain rule. So we talked a little bit about the pre-class video how the help one sense that's the chain rule, upgrading this, having variable rate. And if you need to take derivatives, kind of both paths. So you need to take a derivative with respect to x and with respect to y, and multiply those by the derivative with respect to
have the volume on here. That's worse.
Oh, you click on your iPad, it looks like it's joined. On an iPad.
Oh, that's a good idea. Testing, testing. That's better. All right, good idea. All right. So yeah, for the pre-class video stuff, well, I don't need to spend too much time going through this, but again, you're going to be taking derivatives with respect to x and with respect to y, and then taking the derivative of those with respect to t, and you need to add those results together. And then we got some practice doing exactly that. And you just be careful with these. And what we wanted to start talking about in the in-class portion are these tree diagrams and how we can use these to figure out other versions of the chain rule, depending on how many variables you have. So it will not always be the case that you're just having z as some function of x's and y's, and those are just a function of t. We're going to have s's and t's. We're going to have sometimes w is a function of x, y, and z, right? So we're going to have all sorts of different situations, and we're going to develop the chain rule for all of these. So that's the pre-class video in a nutshell. Any questions about this before we jump into the new stuff? All right. Well then, here we go. Let's upgrade and start talking about what happens if you have some function w that relies on x, y, and z. This is going to be a relatively nice function. It's differentiable. And then those things all rely on another variable, t. So in this case, we're going to have the partial of w with respect to x times the derivative of x with respect to t. So that deals with all of the x's, how the x's may be changing with respect to time. You also need to include in how are the y's changing with respect to time. And this is very similar to what we had in the pre-class video. But now, again, w relies on not just x and y, but x, y, and z. So probably, as you would suspect, right, we need to also take the derivative of w with respect to z times the derivative of z with respect to t. So we need to kind of go throughout all of the different situations here and add those together. Just as a small note, I'm going to try to be good about this in large, but I typically we're not so picky. But when you have a choice about what your derivative is, that's a partial derivative. So you can see I have the partial notation here of w with respect to x. But right, when I start taking the derivative of x, it only has the t variable that it relies on. So then this right is the kind of back in the Calc 1 days, it's the derivative of x with respect to t, but it's not technically a partial derivative because again, you don't have a choice. There's only one variable that it relies on. So, but later on, we're going to get into a situation right here where x does rely on multiple variables, right? It depends on either s or t. And so in that case, if you're interested in a derivative now with respect to t, and again, our z function here relies on both x and y, we're going to take a derivative of z with respect to x, and then a derivative of x with respect to, and right now we're interested in t. So again, this is a partial derivative now, just even up here, the dw dt, right? The final variable, there wasn't choice, there was only t's. But here now you really do have a choice. We can take a derivative with respect to t or with respect to s. Well, we also need to go down the y path as well. So we need to take a derivative of z with respect to y times a derivative of y with respect to t. And now we can play the same game, but now we'd like to end with s rather than t. So a derivative of z with respect to x times a derivative of x with respect to s. And our y stuff. This is using the partial notation, but if you like the subscript notation, by all means, you can use that as well, right? So this would just be z sub x times x sub s, z sub y times y sub s, right? So again, we're doing some partial derivatives. If you'd like that notation, by all means, you can use that instead. So in this case here, z is called the dependent variable. S and t, kind of at the bottom of the chain here, these are the independent variables. And then we have a new class of variable, one that's kind of in between our independent and our dependent, and these are called intermediate. A reasonable name. And again, I personally remember these with tree diagrams. So let me showcase kind of what these instances look like here with the tree diagrams. I'm going to switch to blue. So in our first case, we had W, and W relied on X, Y, and Z. So again, we had some statement, and I'll scroll back up here just so everyone remembers, that W is a function, and it relies on X's, Y's, and Z's. Now, each one of those, the X's, the Y's, and the Z's, they're all functions that rely on T. So again, the function notation here, X of T, Y of T, Z of T, right? So they all rely on what maybe the time is or something like this. So they all rely on T. So if I want to take the derivative of W with respect to T, we need to start off at W and end every place right where we have a T. So in this case, there are 3 different branches that we could go down that would end up at T. There's a branch, right, that goes through X, there's a branch that goes through Y, and there's a branch that goes through Z. And if we're using like the subscript notation, right, this would be W sub X, right? Again, a partial derivative of W with respect to X. And here again, it really, technically you wouldn't be using the subscript notation here because again, there's only one variable. So it's a bit strange, but this is a derivative of x with respect to t. So in that sense, it makes sense. But I mean, you could also just say this is x prime, right? Because again, there's only one thing to take a derivative of, and that's t. Then we're going to go down the next branch, derivative of w with respect to y, and y with respect to t. And then finally, a derivative of w with respect to z, and z with respect to t. Likewise, you could use the partial notation here as well, the Leibniz notation. So again, looking at this, we have our three different branches. And notice that while you're traveling along a branch, you just multiply. So you're going to have your partial of w with respect to x times your derivative of x with respect to t. That's going down this first branch here. Going down the second branch, all the y stuff. Going down the third branch, all the z stuff. And again, you just add branches together. So this also kind of indicates if you had even a more horrible situation where you had like two levels of intermediate variables, right? This is the same sort of game you would still be playing. Let me also show you what the tree diagram looks like in the second case here. So we have z that relies on x's and y's. And then those x's and y's, they both rely on s and t. So if I'm interested in a partial derivative with respect to t, I want to go down, starting at z, all the branches that end with t's. And again, there are a bunch, each one of these little segments is a derivative. So a derivative of z with respect to x, and a derivative of x with respect to t. Starting a new branch, we would add, and we'll have a derivative of z with respect to y, and then a derivative of y with respect to t. And again, while you're traveling through the branch, right, you multiply, and then when you switch over to a new branch, you add together. So that would be this first one right here. Again, only two branches that ended with t. One went through x, one went through y. And then finally, if you wanted to do the derivative with respect to s, right, you're going to be traveling these branches. All right, so again, I wouldn't recommend necessarily memorizing all, each individual character rather than understanding kind of how these things are developed. Any questions so far? All right, well, example time then. I would like to find the partial of z with respect to s and the partial z with respect to t. We can see here that it looks like z in this case relies on thetas and phis, and then theta and phi both rely on s and t. So if I was to draw the tree diagram really fast for this, I'd have z relies on theta and phi, and then each one of these rely on s's and t's. So in the first case, if I'm interested in finding the partial derivative of z with respect to s, I'm going to be interested in traveling down these two branches here. So partial z with respect to s, we'll have the partial of z with respect to theta, and then theta with respect to s. Starting a new branch, derivative of z with respect to phi, and the derivative of phi with respect to s. Again, if you like the subscript notation, you can certainly use that. I'm just kind of going back and forth on these things, so that way you hopefully become familiar and happy with either one, right? No matter how it appears on a quiz or an exam, you need to be able to understand, right? These are both just notations for, hey, take the derivative. Okay, so let's go ahead and take our derivative of z with respect to theta. So I'm looking up here and I see, right, we have a sine theta. So when I take the derivative of that, I'm going to get cosine theta. And that's the only theta, right? Everything else has phi's in it. So those are just along for the ride. Those are independent. Next up, I need the derivative of theta with respect to s. So I'm looking at my theta equation now. Taking a derivative with respect to s, this is going to be 1 times t squared, because the derivative of s is going to be 1 in this case. And then the t squared is constant. It's along for the ride. Starting a new branch. So let's go ahead and add. We need to have the derivative of z with respect to phi. So again, I'm going back and looking at my z equation. I'm going to take the derivative with respect to phi this time. So I'm going to have what my sine theta is along for the ride, and the derivative of cosine is going to be negative sine phi. And then finally, the derivative of phi with respect to s, we're going to have 2s when I take the derivative of s squared, and that t is along for the ride. It's constant. Now, when you do these problems similar to, in calculus 1 and whatnot, it's good to have the answers all in terms of your independent variables. So the fact that my answers here have some of these intermediate variables, I would go ahead and swap these out. So instead of theta, for instance, I'm going to put st squared. And instead of phi, I'm going to put s squared t. Take that, multiply it by my t squared. And let's see, minus, and we have a 2st sine of theta, which again is st squared, and sine of phi, which is s squared t. This is also consistent with what WebWork wants from you as well. So when you go and you type these things into WebWork, right, you're going to want to have all of your independent variables when you type those in. All right, well, let's go ahead and do our partial of z with respect to t now. My claim is, I'm going to cheat a little bit using technology, so I apologize for those of you who don't have this luxury. But I'm going to copy and paste. And in my first line, all right, we want to end with t now. So basically, I'm just swapping out, and notice that my derivatives of z with respect to theta or phi stay exactly the same. I'm just going to be taking my second bit, right? I need to take a derivative with respect to t, which means that these parts right here I'm going to erase, but my derivatives of z with respect to theta and with respect to phi are still good. I'm not changing those at all. So now if I take the derivative of theta with respect to t, I'm going to have 2st. And if I take the derivative of phi with respect to t, I'm going to have s squared. So now in my last row here, this one's going to have the 2st, and this one's going to have the minus s squared now. The reason why, I do this even in class, with the copy and paste, not only to save some time, but also, right, when you encounter something like this in your WebWork homework, notice that you can pull off the same trick with your, computer, highlight it all, copy, paste, and then just change a few things, right? You don't need to rewrite it out from scratch each time. That's just asking to make some small, silly mistake to type an S instead of a T or something like this. So use this trick even when you're doing the homework or whatnot. It's copy and paste and then just change a few little things. Also, I highly recommend using the answer preview. So that way you can kind of see it written out all nice rather than just looking at a bunch of typed text. All right. Any questions on this one here? Oh, sorry. Yes.
Just like in general, how often do you actually if you were a student doing these problems, how often would you draw a tree diagram?
How often would I draw a tree diagram if I was a student doing these problems? I mean, I would do them Maybe you'll just get so good that you don't even really need it, sort of deal. But you know, especially when I have them not relying on X's and Y's or something like this, but you know, a bit of strange variables, I would draw it out just kind of out of habit, right? And this only took me maybe 10 seconds. So it's not like it's a big time sink or anything like this. So it's a good kind of insurance policy that you haven't forgotten some path. Good. Any other questions? Okay. Well then, why don't we go ahead? And I'd like to get you guys in the game a little bit. Slightly different situation. I haven't told you what these functions are. I've only given you basically a table of results, what happens when you plug in certain things. And so this would maybe make a fine multiple choice style question, or if I gave a potential answer, right, that maybe a true false style question. But please try to find this dz dt at the specific time. So when t is equal to 3. So again, I would recommend a tree diagram, but you know, if you're kind of over that, you don't need to have it necessarily, but I do think it helps. So again, maybe 60 seconds, 90 seconds, get as far as you can, and then we can start going over the results together. All right. Well, I've found a few people with looks like a good answer. They were getting 62. Maybe if you got that as well, I think that's correct. But let's go ahead and solve this one together now. So again, a quick tree diagram. Z relies on X's and Y's. And the X's and the Y's, they both rely on T. So this is kind of the classic, really straightforward one here. So if I wanted to find the derivative of Z with respect to T then, I'm going to have the derivative of Z with respect to X times the derivative of X with respect to T plus the derivative of Z with respect to Y times Y with respect to T. And again, the Y's and the X's, they only rely on T, right? So when I use the prime notation, there can be no confusion because they only rely on T. So that means a derivative with respect to T. But if you want to use the subscript or whatnot, you can do that as well, but just kind of staying consistent up here. So we see the prime notation because again, these things only rely on T. The other thing is that this decides to use, right, rather than Z, remember Z is a function of X's and Y's, so it uses F rather than Z. Okay, fine. So I can go ahead and maybe start plugging some of these things in. So for instance, I'm going to have my partial derivative with respect to X is supposed to be 6. And my partial derivative, my derivative of X at the special time, right? I'm interested when T is equal to 3. I get 5. The derivative of Z with respect to Y, or F with respect to Y, that's going to be -8. And then the derivative of Y is going to be -4. So I guess the only, we can get the correct final answer here. 30 plus 32 is going to be the 62. But maybe my question is, what's up with this 2 and the 7 here? I thought we were supposed to be taking a derivative at 3. How are those 2 and the 7 coming into this? Yeah. Yeah, so remember our function eats x's and y's, right? So you have a hard time feeding it t equals 3. You have to feed it an x and a y value. And so that's where this extra piece of information here that seemingly was unused, except for the fact that, it guarantees that, yes, we are interested in when x is 2 and when y is 7, because that's what they're doing at time 3. At time 3, x is 2 and y is 7. So that's why you have the 2 and the 7 there. All right. Any questions on this one here? All right. So then we're going to switch gears and talk about a new way to do implicit differentiation a bit better. So I'd like to first off go back to our days of calculus 1 and suppose that x and y are not independent variables anymore. Again, back in calculus 1, quite often they relied on one another. So y was quite often a function of x. Here they are related via this curve right here, x cubed plus y cubed is equal to 6xy. And I'd like to find the derivative of y with respect to x. Again, they rely on one another, using the old Calc 1 way. So if I was to do this using the old Calc 1 implicit differentiation, and I'm taking a derivative with respect to x, well, the derivative of x cubed then would be 3x squared. That one's relatively straightforward. The derivative of y cubed, and again, we're taking the derivative of y with respect to x, right? So y cubed with respect to x. So when I take the derivative with respect to x, really what we have is a bit of a chain rule situation here. So the 3 comes down, reduce our power by 1, leave the inside alone. So the inside, in this case, we have the y function. Then you multiply by the derivative of the inside. So the derivative of y, and again, we're taking a derivative with respect to x. So this would be dy dx. Technically, you can even do this for the x's over here. But then again, we're taking the derivative of x with respect to x, right? And so this is going to be 1. The derivative of x with respect to x is 1. So that's why we don't typically do this. But if you want to use the small chain rule here, you could. Okay, and then on the right-hand side, right, we have a product because again, x and y rely on one another. So we're going to have the derivative of the first times the second plus the first times the derivative of the second. And again, we're doing a derivative with respect to x. So the derivative of y with respect to x is going to be dy dx because again, these things are relying on one another. So now if I'd like to solve for dy dx, typically what I used to do in our Calc 1 days is I gather up all of the dy dx's on one side and I put everything else on the other side. So why don't we go ahead and write this as maybe 3y squared dy dx minus 6x dy dx is equal to 6y minus 3x squared. So again, just adding and subtracting things to try to gather all of my dy dx's onto one side. Once I have that, I can factor out. So I have dy dx times this stuff here. Oops. And then finally, if I'm interested in solving for dy dx, the last thing I need to undo this multiplication to get dy dx all by itself. So of course I'm going to divide. So dy dx is equal to 6y minus 3x squared divided by my 3y squared minus 6x. So using the Calc 1 method, this would be our final answer. Unless if I made a mistake.
If we first get all the y's to one side and then differentiate?
What if we first get all of the y's to one side and then differentiate? You would be fine except for, the fact that you're going to have a product rule here. So when you take the derivative, not all of your terms are going to have dy dx. So you're still going to need to move that one term over to the other side. So it's kind of, you haven't so much saved steps. You still need to kind of put You're right, because you'd get all of your y's onto one side here, and then you'd still need to move one term over. So again, you still need to kind of move a couple of terms over to the other side. So that works, but it's not any faster, I guess. Okay, so now I'd like to show you a cool trick here using the Calc 3 chain rule, and a way that we can calculate out this dy dx a little bit faster, I'd say. And this relies on us getting all of our functions on, all of our variables on one side and a constant on the other side. So we're going to get basically an implicit surface set up here. And again, assuming that y, is implicitly relies on x. So again, they're not independent in this case. It makes sense to say dy dx, and the answer is just not 0 sort of deal. Then the claim is that this is going to be equal to negative f sub x divided by f sub y. And I'll showcase the same example again and hopefully convince you that it's a bit faster. But let me give you an idea of why this is the case. So if I take the derivative, of this f function. So I have this capital F function. We've already said that it relies on x and y. And now the thing is that y is not independent from x, right? Y actually depends on what x is as well. So we could do something like this. In fact, I guess x relies on x. So if you really want the trees to have the same length branches or whatnot, you could do something like this. So then using the Calc 3 chain rule, we're going to get this line right here. We're going to take the derivative of f with respect to x, and then take the derivative of x with respect to x. Then we're going to take the derivative of f with respect to y, and then the derivative of y with respect to x. And again, ultimately, right now, what we're trying to get is the derivative of y with respect to x. So then we can rearrange, and you can kind of see where this negative sign comes from, putting that on the other side. And then we can divide, and we're going to get our final answer that dy dx is going to be equal to this, again, negative of the quotient of these partial derivatives. So this is, again, an idea of the proof of why this should work. Now I'd like to showcase, right, that we really do get the same answer if we apply this to that same problem. So again, the setup for this is that we need to gather all of our variables on one side, and we need to get a constant on the other. So I'm going to write this as x cubed plus y cubed minus 6xy equals 0. 0 is a perfectly nice constant. But again, there could be a 3 over there, there could be a 12 over there, it doesn't matter, right? So long as you get all of your variables on one side and a constant on the other side. Because then this right here is going to be our f. That's the thing that we're going to be taking partial derivatives of. And now, again, we're back into our Calc 3 mode, where we're pretending that x and y don't rely on one another, right? That they are independent from one another. We're taking partial derivatives, right? So in partial derivatives, right, again, they do not rely on one another. So I'm going to calculate out my f sub x and my f sub y. So the partial derivative of f with respect to x is going to be my 3x squared minus 6y. And my partial derivative of f with respect to y is going to be 3y squared minus 6x. And so according to this theorem, we have dy dx ought to be equal to negative, and then we have the partial derivative of f with respect to x divided by partial derivative with respect to y. And so if we look back here, okay, well, the bottom is exactly what it's supposed to be, 3y squared minus 6x, 3y squared minus 6x, but we need to distribute this negative to each piece here. And so when we do that, right, we're going to have a negative here and a plus here. So plus 6y and negative 3x squared. exactly the same. So notice that this one did not rely on us kind of rearranging and collecting all of the terms or anything like that. Any questions on this? So, okay, this is cool, and it's, you know, a bit of an upgrade for an old Calculus 1 question. But I mean, one natural thing is, how can we expect to use this in Calculus 3, right? How would this be showing up for a Calculus 3 style problem? So for a Calculus 3 style problem, now pretend you have a function that relies on x's, y's, and z's. And again, you gather all of your variables on one side and you have a constant on the other side. If you're interested in getting a partial of z with respect to x, this is going to be negative f sub x divided by f sub z. And if you're interested in getting a partial derivative of z with respect to y, negative f sub y divided by f sub z. And the nice thing about this is that in 14.3 and in 14.4, whenever we were taking derivatives, partial derivatives, right, z with respect to x or with respect to y, we always needed to have a z equals equation, an explicit equation where z was a function of x's and y's. But with this, my claim is you can have z's scattered all around the equation. You do not need to have a z equals anymore. You can have it kind of an implicitly defined function where z again relies on x's and y's, but maybe it's not an explicit function. And yet still, we're going to be able to find partial derivatives with respect to x and with respect to y. All right, so with that, I hope you see why this is an upgrade and how this helps us with some Calc 3 problems. Maybe please take 2 minutes or so, try to apply this to our problem here. Another 30 seconds or so. Again, get as far as you can. All right, so again, the main setup for this, in order to apply this rule, you need to have all of your variables on one side and any old constant on the other side. And so I've given us two different ways that we could successfully do this. We could divide by z squared and get a 1 on the right-hand side. We could also just subtract away the z squared and get a 0 on the other side. And my claim is that so long as you do both of these carefully, you should be able to get the same answer at the end of the day. Of course, one of these is much easier than the other, right, to actually take derivatives of in practice. So we're going to primarily be doing a lot of subtraction, right, to get all of our variables onto one side. But if you wanted to be, if you wanted to give yourself a bit of a challenge, you could do, division, things like this. So, all right, let's go ahead and do it maybe the straightforward way that we would probably, I hope, would do it for a quiz or an exam or something like this. So now I know what my f function is. And this is the thing that I need to take partial derivatives of. And then we're going to combine those partial derivatives and get our final result. So if I take a derivative with respect to x, I think I just get natural log of y. If I take a derivative with respect to y, I think we're going to have what? Z plus x divided by y. Because again, the derivative of the natural log is 1 over. So it's 1 over y in this case. That x is along for the ride. And then finally, if we take the derivative with respect to z, what we're going to have y plus 0 minus 2z. So there are my components that I need. And remember, in order to get our partial derivatives, we just need to take ratios of these things and sprinkle in that negative. So if I want the partial derivative of z with respect to x, this is supposed to be my f sub x divided by f sub z with this negative. So it's going to be the negative natural log of y divided by y minus 2z. If I want the derivative of z with respect to y, negative f sub y divided by f sub z. So what we're going to have negative z plus x over y divided by y minus 2z. Those should be my final answers. Liking this stuff more than Wednesday's class? Good. Question.
F of y are negative.
Sorry, one more time.
Why is f sub x and f sub y negative?
F sub x and f sub y negative. So it's the same. So I could start with, it comes from the formula. Why this negative exists in the formula is the same reason, right? We'd have to draw a slightly different tree diagram here. But we'd have f relies on x, y, and z, and then z relies on x and y, right? And so then we would do the tree diagram and go through all these different paths. But moving the one side over is what's going to get this negative sign. So very similar to the two-dimensional case. All right, one more here. Why don't we do this one together? So again, I need to find my f function, and I'm going to take derivatives with respect to x and with respect to y, because after all, we know that dy dx is equal to negative f sub x divided by f sub y. So the first question that we have to ask ourselves, well, what is this f thing? Which I understand is an easy question, to get right today's class. The trick is to really remember it for the final exam and all that sort of stuff. So again, f comes from moving all of your variables to one side and getting a constant on the other side. So I'm going to go ahead and maybe range this as 0 is equal to x plus xy minus e to the y sine x. Of course, you may choose the opposite, right? You may say, I'm going to move all my variables to the left-hand side, right? And yet still we'll get the same answer at the end of the day, because basically we're both going to have, we'll be off by two negatives, right? One for our f sub x, one for our f sub y. And so those negatives will perfectly cancel out. But, it's a worthwhile thing to check. So, I mean, if you want a little bit more of a challenge, put it all on the left-hand side and verify that we do get the same answers. So now this thing right here, this is my f. This is my function that has all my variables in it. This is the thing that I want to take the derivative with respect to. So my derivative with respect to x, we're going to have 1 plus y. The e stuff's along for the ride. The derivative of sine is cosine. The derivative of the y, with respect to y here, we're going to have 0 plus x minus the derivative of e is itself, that sine x is along for the ride. And so my final answer is negative 1 plus y minus e to the y cosine x divided by x plus e to the y sine x. Minus, thank you. Yep, minus e to the y sine x. All right, well, we made it through the notes. I feel like it's been a while since I've done that, so that's always nice. I'll stick around if there are any one-on-one questions. Otherwise, enjoy this extra 3 minutes or so of freedom or weekend or whatnot. I'm sure I will use that 3 minutes up next week or something on other topics. So, all right, take care. Again, I'll stick around for any extra questions.